C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 8. Now, let's talk about Chapter 8, Managing Context Windows Locally. Moving on to theoretical foundations. The fundamental challenge of running large language models locally is not computational power, but the scarcity of high-bandwidth memory, VRAM, relative to the model's appetite. In a cloud environment, we abstract away memory constraints by scaling horizontally. Locally, we are bound by the physical limits of our GPU. This section establishes the theoretical bedrock for managing these constraints, focusing on the interplay between context windows, token budgeting, and semantic pruning. Moving on to the finite journal, a tale of context and memory. Imagine you are a historian, the LLM, writing a collaborative book with a scribe, the user. Your desk is incredibly small, this is your VRAM. You can only keep a few pages of the current chapter open at once. If the conversation, the book, goes on for too long, the desk becomes cluttered. You cannot fit the new page the scribe hands you because the old pages are taking up all the space. This is a context overflow. To solve this, you have a few strategies. 1. The sliding window, you slide the old pages off the desk into a box, system RAM/disk, to make room for the new ones. You only remember the last few pages vividly. 2. The executive summary, instead of keeping every page, you take a moment to summarize the previous pages into a single, dense paragraph, vector embeddings. You pin this summary to the top of the desk. It takes up very little space but retains the gist of the history. 3. The token budget, you strictly ration how many words the scribe is allowed to write per turn to ensure you never run out of desk space. In C# ONNX runtime, we are the scribe's manager. We must implement these strategies programmatically to ensure the conversation flows without the GPU throwing an out-of-memory exception. Now, let's explore the architecture of scarcity, token budgeting and sliding windows. The core unit of memory in an LLM is the token. It is not a word, it is a chunk of data. A model's context window is the maximum number of tokens it can attend to in a single forward pass. This includes the system prompt, the user input, and the model's previous output. When we run locally, we cannot simply rely on the model's native context window, e.g., 4096 or 8192 tokens, because the weights of the model itself already occupy the majority of the VRAM. The activations, the intermediate calculations, consume the rest. Let's discuss token budgeting. Token budgeting is the act of strictly enforcing a limit on the total tokens processed in a single inference step. This is not just about truncating text, it is about intelligent allocation. In a modern C# architecture, we treat the context window as a finite resource pool. We use interfaces to abstract the source of tokens, allowing us to inject budgeting logic transparently. This relates back to Book 7, Chapter 4, where we discussed the iModel connector interface. Just as that interface allowed us to swap between OpenAI and local Llama implementations, we will use a iContext Manager interface here to wrap our model inference, ensuring that no call reaches the ONNX runtime without passing through our budgeting logic. Turning our attention to sliding window attention. Standard transformer attention is $O(n)² with respect to sequence length. If we have 10,000 tokens of history, the model attempts to calculate the relationship of every token to every other token. This is computationally expensive and memory intensive. The sliding window attention mechanism restricts the attention head to only look at a fixed window of previous tokens, e.g., the last 512 tokens. However, we still need to preserve the information of the tokens that have slid out of the window. This is where the distinction between raw history and compressed context becomes critical. Let's discuss semantic pruning, the librarian's index. When the sliding window forces us to discard old tokens, we lose nuance. To mitigate this, we employ semantic pruning using vector embeddings. The analogy: imagine a librarian, our C# application, managing a vast archive, the conversation history. The user asks a question about a topic mentioned 50 turns ago. The librarian cannot read every past page to find the answer, too slow. Instead, the librarian has an index, vector database, where every past conversation is converted into a mathematical vector, a set of coordinates in high-dimensional space. 1. The user's new question is converted into a vector. 2. The librarian looks for the closest vectors in the index, cosine similarity. 3. The librarian retrieves the actual text of the closest matches and injects them into the context window as past context. This allows us to recall information from gigabytes of past conversation while only using a few kilobytes of VRAM for the current inference. Now, let's talk about the C# ONNX runtime pipeline, structuring the flow. To implement this in C#, we rely heavily on records and pattern matching. Records provide immutability, which is crucial when dealing with conversation history to prevent accidental state corruption. We define the state of our context manager as a record containing 1. The active window, a list token of the immediate history required for the sliding attention mechanism. 2. The semantic index, a collection of vector embeddings representing the forgotten history. 3. The token budget, an integer representing the maximum capacity. Here is the conceptual structure of the data we manage. Here, we're bringing in essential namespaces. System, collections, generic is a foundational part of C# for working with collections like lists, which are crucial for managing sequences of data, such as conversation turns or historical embeddings. System, numerics, tensors is a hypothetical namespace, but it's included to represent the need for efficient numerical operations, particularly with vectors. In a real-world scenario, this would likely be a library like System, Numerics, Tensors, which is in development for .NET 8+, or a third-party library like TorchSharp or TensorFlow.NET for high-performance tensor and vector computations, which are indispensable for AI workloads like embedding generation and similarity searches. Without such a library, vector operations would be significantly slower and more complex to implement manually, impacting the real-time responsiveness of our AI. We're defining a record called conversation state. Records, introduced in C number 9, are a fantastic choice here because they provide immutable reference types with value-based equality. This means that once a conversation state object is created, its properties, active context, historical embeddings, token budget, cannot be changed directly. This immutability is a best practice for state management, especially in concurrent or complex systems, as it prevents unexpected side effects and makes reasoning about the system's state much easier. If we were to use a traditional class here, we'd need to manually implement deep cloning or defensive copying to ensure immutability, which adds boilerplate and potential for errors. The active context will likely store the recent textual turns of a conversation, while historical embeddings will hold the vector representations of past interactions, enabling semantic search and context retrieval. The token budget is critical for managing the input length to large language models, preventing overflow and controlling computational costs. This block introduces the iVectorStore interface. This is a crucial architectural decision for achieving separation of concerns and promoting testability. By defining an interface, we're abstracting away the concrete implementation details of how vectors are stored and retrieved. This means we could swap out different vector database technologies, e.g., Pinecone, Weaviate, Face, or a simple in-memory store, without altering the core logic of our application. The store method is responsible for taking an embedding, a numerical vector representation of text, and its corresponding text, and persisting it. The retrieve method is designed to take a query embedding and return the top k most semantically similar text snippets from the store. This top k parameter is vital for controlling the amount of context returned, balancing relevance with the LLM's token budget. This interface is the backbone for implementing retrieval-augmented generation, RAG, a powerful technique for grounding LLMs with external knowledge. Turning our attention to the dynamic pruning logic. The pruning logic is where we apply our constraints. We simulate the process of evaluating the context window. When the sum of tokens in active context exceeds the token budget, we must perform a merge or eviction. We utilize pattern matching to decide the fate of a token block. 1. If the block is a system instruction, it is high priority. We keep it, reducing the budget for user history. 2. If the block is user history, we calculate its semantic density. If it is fluff, low information density, it is pruned immediately. 3. If the block is high-value history, we generate an embedding for it, store it in our iVectorStore, and remove the raw text from the active window. This process ensures that the active context passed to the ONNX runtime is always lean and within the hardware limits, while the historical embeddings serve as a compressed long-term memory. The diagram depicts the context management pipeline, where the active context is pruned to meet hardware limits before being passed to the ONNX runtime, while historical embeddings act as a compressed long-term memory source. Let's discuss architectural implications for C# developers. When building this, we must be aware of the garbage collector, GC, pressure. VRAM management in C# ONNX runtime is distinct from managed memory. If we are constantly creating new arrays for tokens or embeddings, we might cause Gen 2 GC collections, which pause the application. To mitigate this, we use span T and arraypool T as standard in modern C#. We rent buffers for tokenization and vector operations, use them, and return them immediately. This keeps the managed heap clean and focuses the memory pressure on the VRAM, which is the actual bottleneck. Furthermore, we must handle streaming. In a local setting, we often stream tokens to the UI to reduce perceived latency. Our context management must be thread-safe. We will likely use concurrent Qt for the ActiveContext window to allow the background inference thread to push generated tokens while the UI thread might be adding user inputs, all coordinated by semaphore slim to ensure we don't re-enter the inference engine while it's already running. Let's discuss theoretical foundations. We have established that, 1. VRAM is the bottleneck, not compute. 2. Token budgeting is a hard constraint we must enforce programmatically. 3. Sliding windows manage immediate attention scope. 4. Semantic pruning, via vector embeddings, allows us to maintain long-term coherence without storing raw text in VRAM. 5. Modern C# features like records, pattern matching, and span-t are essential for building a performant, memory-safe context manager. In the next subsection, we will begin implementing the Context Manager class, focusing on the tokenization and budgeting logic using Microsoft.ml.onks runtime. Now, let's talk about basic code example. Here is a simple, self-contained example demonstrating how to manage a limited context window in a local LLM scenario using a sliding window approach and vector embeddings for semantic relevance. We begin by importing necessary namespaces. Notice Microsoft.ml.onks runtime and Microsoft.ml.onks runtime, tensors. These are critical for interacting with ONNX, Open Neural Network Exchange, models, which is the format we typically use for deploying pre-trained AI models like embedding generators or even smaller LLMs locally. System numerics is included because it provides types and methods for numerical operations, which are often useful when dealing with vector mathematics like those found in embeddings. The other system namespaces provide fundamental types and collections for general C# programming. Here, we define our local context management namespace which logically groups related code. Inside, we have a record type called conversation message. Using a record is a modern C# feature that provides concise syntax for creating immutable data types, which is excellent for representing messages in a conversation history. Each message has a role, e.g., user, assistant, system, the actual content of the message, and crucially, an embedding. This embedding is a float, representing a numerical vector that captures the semantic meaning of the message. This is a core concept in AI for understanding text relationships. We introduce the Context Window Manager class. This class is the brain of our local context management system. It's designed to manage the conversation history and intelligently select relevant messages for an LLM, especially when the total conversation length exceeds the LLM's input token limit. The _max token budget field is a vital constraint, representing the maximum number of tokens our target LLM can process in a single input. The _history list stores all conversation message objects. The constructor simply initializes this budget. Notice the comment at line 19. It highlights that in a real-world scenario, we would integrate with an actual embedding model, but for this example, we're simulating that part. The addMessage method is how new messages are incorporated into our conversation history. Observe at line 30 that we call generate mock embedding, content. This is where the magic of semantic understanding begins. In a production system, this call would involve passing the content to an ONNX-based embedding model, like all, mini-LM, L6, V2 or BG, small, n, V1.5, which would return a dense vector representation of the text. For this example, we're simulating it. The generated embedding, along with the role and content, is then encapsulated in a conversation message record and added to our _history list. This ensures every message we store has its semantic fingerprint readily available. This get-optimized context method is the core logic for intelligent context pruning. It takes the current query from the user as input. At line 39, we log the current history size for debugging and observation. Then, at line 42, we perform a crucial step, approximating the total token count of the current history. We use a heuristic here, 1 token equals 4 characters for English text. This is a simplification. A production system would use a proper tokenizer, like sentence piece or BPE, to get an accurate token count. If the current tokens are within our _max token budget, we can simply return the entire history, saving computational resources. If the current conversation history exceeds our _max token budget, we must prune it. Line 50 clearly indicates this. The first step in intelligent pruning is to understand what the user is currently asking. So, at line 53, we generate an embedding for the current query. This query embedding will be our semantic anchor. We'll use it to determine which historical messages are most relevant to the user's immediate need. This is a fundamental technique in retrieval augmented generation, RAG, and semantic search, where you find items, in this case, messages, that are semantically close to your query. With the query embedding in hand, we now score each message in our history based on its semantic relevance to the current query. Look at lines 57 to 61, we select each message and calculate its score using calculate cosine similarity. Cosine similarity is a standard metric for measuring the similarity between two non-zero vectors in an inner product space. A value close to 1 means the vectors, and thus the texts they represent, are very similar in meaning, while a value close to 0 means they are orthogonal, unrelated. By order by descending, x equals x.score, we prioritize the messages that are most semantically aligned with the user's current intent. Now we implement a sliding window approach to reconstruct the context while respecting the token budget. We initialize an optimized context list and accumulated tokens. We iterate through the scored history, which is already sorted by relevance. For each message, we estimate its token count, line 71. If adding this message keeps us within the underscore max token budget, we include it in optimized context and update accumulated tokens. This greedy approach ensures we fill the budget with the most relevant messages first. This is a practical compromise. A more sophisticated approach might use dynamic programming to find the optimal set of messages, but for many real-time applications, this greedy selection is efficient and effective. This else block at line 78 is crucial for budget enforcement. If adding the current message, which is the next most relevant one, would exceed our underscore max token budget, we simply break out of the loop. This means we stop adding messages, even if there are other relevant ones further down the scored history list. This ensures that the optimized context never surpasses the LLM's input limit, preventing errors or truncated responses from the model. This is a hard constraint for LLMs, as exceeding their context window can lead to unpredictable behavior or outright failure. After selecting the most relevant messages, we perform a final reordering step at lines 87 to 89. While semantic relevance is key for selection, LLMs often perform better when the conversation flow is chronological. So, we order by m equals underscore history.index of m to restore the original temporal order of the selected messages. This ensures that the LLM receives a coherent narrative, even though some less relevant messages might have been pruned from the middle. This is an optional but usually preferred step because it enhances the LLM's ability to maintain conversational continuity. Finally, we log the results and return the final context. Here we have generate mock embedding, a helper method that simulates the output of an actual embedding model. Notice at line 101, we use new random text.getHashCode. This makes the mock embedding deterministic for a given text, meaning the same text will always produce the same mock embedding. This is useful for consistent testing. The method creates a float array of size 384, which is a common embedding dimension, e.g., for all mini-LM L6 v2. Each element is filled with a random float. In a real application, this method would be replaced by an ONNX runtime inference call to a pre-trained embedding model, which would convert the input text into a meaningful numerical vector. The calculate cosine similarity method is another crucial helper, implementing the mathematical formula for cosine similarity. It takes two float arrays, our embeddings, and returns a float representing their similarity. The first check at line 113 is for defensive programming. If the vector lengths don't match, cosine similarity is undefined, so we return 0. We then iterate through the vectors to calculate the dot product, sum of element-wise products, and the squared magnitude for each vector. This loop is the core of the calculation, performing the vector algebra necessary for semantic comparison. After calculating the sums of squares, we compute the actual magnitudes by taking the square root at lines 126 to 127. A critical check follows at line 129. If either magnitude is 0, it means one of the vectors is a 0 vector, which would lead to division by 0. In such cases, we return 0, indicating no similarity. Finally, at line 130, we compute the cosine similarity by dividing the dot product by the product of the magnitudes. This yields a value between -1 and 1, but for embeddings, it's typically between 0 and 1, as embeddings are often normalized and positive-oriented, where 1 signifies identical direction, maximum similarity, and 0 signifies orthogonality, no similarity. We define the program class, which contains our application's entry point, main. At line 138, we instantiate our context window manager with a max token budget of 512. This simulates a common constraint in local LLM inference, where smaller models or resource-limited environments might only accommodate a few hundred tokens. Lines 142 to 145 demonstrate how we populate the conversation history. We're deliberately adding enough messages to ensure the total token count will exceed our budget, setting the stage for the pruning logic to kick in. This setup allows us to effectively test the context window manager's ability to handle overflow. We continue populating the history, adding a longer, more technical discussion about sliding window attention, lines 147 to 150. This content is specifically chosen because it's relevant to the new query we'll introduce later, allowing us to see how semantic relevance helps preserve important context. Then, we intentionally add noise or irrelevant messages, lines 152 to 153, to simulate a natural conversation where topics might drift. This helps confirm that our pruning mechanism can identify and discard less relevant information. Finally, we add more technical detail, lines 155 to 156, to ensure there's ample relevant information to select from. Here, at line 159, we define new query. This is the user's current input, and it's intentionally designed to be semantically related to the technical discussion we added earlier. This is the query against which all historical messages will be scored for relevance. Lines 161 to 162 print a separator and the query itself, making the output clear. Then, at line 164, we call contextManager.getOptimizedContext, new query. This is where all the logic we discussed earlier, token counting, embedding generation, cosine similarity scoring, pruning, and reordering, is executed to produce a concise, relevant set of messages. Finally, at lines 167 to 171, we simulate passing the optimized context to an LLM for local inference. In a real application, this for each loop would construct the prompt string that is then fed into an ONNX runtime session to query a local LLM. The output here clearly shows which messages were selected by our context window manager and in what order. This allows us to visually verify that the most relevant messages, e.g., about sliding window attention, were retained, while less relevant ones, like the breakfast query, were likely pruned, demonstrating the effectiveness of our semantic context management strategy. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 8 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.